Hello and welcome to the second video accompanying handout 7 on the topic of normalizing the Schrödinger equation. All right, so this first example is a bit of an odd one out from the three examples I've chosen to show you, but I think it helps kind of show what we're doing, why we're talking about differential equations and wave solutions to that equation, okay? So we want to show that the one-dimensional Schrödinger equation reduces to k plus u equals e, which of course is just total energy, right? So it's kinetic energy plus potential energy equals total energy. That's it, right? Because that should be conservation of energy. If there's no other forms of energy here, there isn't for a matter wave, it should be a true statement, okay? So we're going to start with the wave function solution. So here I'm using the full wave function solution for the time-independent Schrödinger equation, the most general form of the Schrödinger equation, right? Because everything else was a special case that we can dive into and is interesting, but that was a special case of an infinite potential energy well, right? Whether 1D or 3D. Okay, yeah, it's true we skipped over 2D, right? But it should be true all the time. It should be true when there is a non-zero potential energy, okay? So we're going to proceed with direct substitution into this differential equation. So all I'm doing here is every time, if you look at the key equations section, and if you watch the video where I go over those key equations, every time there's a psi function, which is a wave function, psi as a product of x, all I've done is just replace the proposed solution, okay? All right, or just replace the variable function with the proposed solution, with its form. Now one thing I do want to talk about, the fact that there is a non-zero potential energy, but yet there is zero potential energy for the infinite well. You might wonder about that. You might not, but I've made a big deal in a lot of my classes. If you had classes with me or listen to my videos for other classes, I make a big deal about the idea of potential energy wells, whether that's a potential energy well of an atom and the electrons that are in that well, such as the ground state of hydrogen with negative 13.6 electron volts, or the idea of standing on the surface of Earth and having a total negative energy because your potential energy is so much larger than your marginal kinetic energy due to Earth's rotation that you are in that gravitational potential energy well. In those cases, it wasn't like the potential energy was zero just because we were at the bottom of a well. It was just a negative value. So why is it now that when we say that we're at a well, all of a sudden it's zero? Why isn't it negative infinity? Because we've chosen, in the case of the infinite well, we've chosen for potential energy to be measured at the bottom of the well rather than at the top. Because that's the thing about potential energy. We always choose where the 0 point is, okay? And when the well is finite, such as Earth's gravitational well, and being, living on the surface of Earth, or a atom with an electron at the bottom of that electrostatic potential energy well, well, in those cases, those finite wells, it made sense to set potential energy as zero at an infinite distance away from the attractive source, whether that's the planet or the nucleus of the atom. But in this case, since there's no way to escape, you're well and truly trapped in that well forever, it makes sense to set potential energy zero at the bottom of the well, okay? So hopefully that's satisfying if you were concerned about that inconsistency. So anyway, so we've done the direct substitution into our differential equation. Then we're just going to go ahead. The only thing we need to do is just take the derivative of this exponential function twice with respect to x. When we do that, exponentials, when you take the derivative, they don't change, but the chain rule says that we have to pull down the ik. So we pull down the ik both times we do the derivative, so it just becomes ik squared because we just do it twice, okay? And then our leading coefficient of negative h bar squared over 2m is still there, all right? And so then the last thing we're going to do is we're going to remember that from our ideas about the imaginary number I, if you square I, you get negative 1. Well, in that case, we'd have negative 1 times k squared times a negative. The negatives would cancel, and we'd be left with h bar squared k squared over 2m plus u equals e. Well, if you remember those very first equations I showed you in the key equations section of the notes, I mentioned that one way to express the kinetic energy is h bar omega, and another way is h bar squared k squared over 2m. Well, there's the other way. So sure enough, kinetic energy is exactly that expression, and then we're left with what we wanted to find. That kinetic energy plus potential energy equals total energy. All right? That's what the differential equation, the Schrödinger equation, is telling us. All right? So good. Now, let's get into Schrödinger equations where u is 0. From now on, that's going to be the case. So let's do our second of two examples. Example 2. Show that the normalization constant for C for the one-dimensional particle in a box is C equals the square root of 2 over L. So I showed you the normalized version of a particle in a box, And I said that it was, that was the case, and then I mentioned that I was going to prove that later in one of the examples. Well, now we're going to do it. Now, if you're wondering why I didn't do something similar for the particle in a 3D box, why I didn't just give you a normalization constant and say, hey, we're going to see it later, is because it turns out that the shape there can matter a lot. The normalization constant is incredibly dependent on, if it's a rectangle, what are the relative lengths of the sides. In the case of the cube, then there kind of is a similar well-known normalization constant that you could easily look up. But I did assign that as one of the homework problems. And in that case, you're going to show what the normalization constant is, but I'm not telling you what it is ahead of time. All right? Either just find it or confirm it with a quick Google search. Okay? So here we're going to start with the wave function solution. Here, since we're dealing with the confined particle in a box, one-dimensional, this is our wave function solution as opposed to example 1, right? So again, that's why I chose example 1, just to make sure we know where things are coming from, right? Of course, it depends what solution we're proposing, but this is the solution for the infinite well. All right. So we proceed with substitution into the probability integral. So since we're not showing the same sort of thing, we actually don't care to substitute directly back into the differential equation. Instead, we want to substitute it into the probability integral. And this is the probability distribution, psi squared, integrated over all values of x. Okay? Well, it turns out that our probability integral in this case is just going to be equal to integrating from 0 to L, because it's impossible to be outside of that 0 to L. And then we could do negative L over 2 to L over 2 as well. It wouldn't matter. Okay? Here we're going negative from 0 to L. And we know that's going to have to be equal to 1. That's the whole point. Okay? So then we just put it in, right? Here I've actually already substituted in. Okay? So here I have the general form of just psi, but here I've already substituted in the particular form that we're proposing. Now, here I do a trigonometric identity substitution. And this will come up because this is a necessary trick to solving these integrals. Because integrating sine squared, if you don't know how to do it, you'd kind of run into a dead end. Again, you could look it up and you'd find in a table of common integrals how to do it. One really good way to do it is do a substitution where sine squared theta equals 1 minus cosine 2 theta. But in this case, theta is kx. Okay? And that's in radians, by the way. Right? It's very important. We're in radian mode. Okay? That's how we're able to use things like wave number, right, and omega. Those are angular quantities that depend on all of our trig functions being calculated in radians. Okay? So that's what we're going to do. This is our form now with our trig substitution. I haven't done anything else in terms of solving the integral. So all I've done is the substitution. Okay, and it's 1/2. The identity is that sine squared theta is 1/2 times 1 minus cosine of 2 theta. Okay. All right. So then I'm going to go ahead and actually do the derivatives of both the functions because they're separated by subtraction. So I can just get away with just doing a very simple antiderivative. Okay. And actually, this should be a 4. I had it as a 4, and then I changed it back to a 2 for some reason. But it should be a 4 because we distribute in the 1/2. So I'm gonna have to fix that a few times. It's a stupid mistake. But if you see, I didn't distribute in the 1/2 here. I distribute in the 1/2, which then when I do the antiderivative, the 1/2 just becomes x over 2. But here I should have a 1/2 times cosine of 2 theta. In that case, when we do the antiderivative, we take the reciprocal of what's due to the sort of the antiderivative chain rule, we take the reciprocal of what's multiplied by x inside the sine function, right? So that becomes L over 2 n pi, but I should distribute in the 1/2, so it should be L over 4 n pi. Okay, so again, this should be 4. All right, doesn't change our answer, however, because that term ends up just zeroing out, but it will matter for one of the homework questions. Okay, so then we're going to evaluate this antiderivative from 0 to L. That will finally give us our integral. That's the whole point, right? So here's the thing. Well, it turns out that when we evaluate this integral, that the second term, the trig term, is going to be 0 for both the upper limit and the lower limit. So for the lower limit, if we plug in x equals 0, obviously sine of 0 equals 0. If we plug in x equals L, then we get sine of n, or 2n pi, which is going to be 0 for all n. Okay? But first of all, where did the n come from? I kind of skipped over that step. So if we look, all I've done is I've replaced the wave number with n pi over L. And that's just because these are standing waves, and you have to have these integer multiples of half a standing wave with that fit within the well. That way you can get a node at either end. So that's all this is saying right here, is you need a node at either end. Okay? So anyway, I've done that substitution, and I wrote everything in terms of n pi over L instead of k. It's more clear, especially in terms of arguing for when the sine function becomes 0 at both the limits. Okay, so hopefully you can clearly see at the upper limit that for all n, that sign is going to be, because it's just an integer multiple, because n is an integer after all, an integer multiple of 2 pi, and sine of 2 pi is 0, sine of 4 pi is 0, and so on. Okay? Thus, our total probability integral just becomes c squared times L over 2, right? Because think about it, because the only thing that was left was evaluating this result of the antiderivative, that of course we got with the trigonometric substitution. So just evaluating that at the upper limit and the lower limit. When you evaluate the upper limit, it's L over 2. When you evaluate the lower limit, it's just 0. And so there you have it, right? That's the total. This right here is the total result of the integral, which is equal to 1. When we solve for c, there we have it. We have our normalization constant, the square root of 2 over L. Good. Excellent. Okay? So this is an important stepping stone because the 1D case is pretty straightforward. But it turns out the 1D case is just that. It's really always going to be just the square root of 2 over L. The 3D case, though, there are infinite possibilities. And let's show why. Okay. So now we're going to find the value of constant c, that's the normalization constant as it's called, that normalizes the wave function for a box with sides Lx equals L, and I had a typo here where I called it 1, but it's supposed to be L. Ly equals 2L, so it's twice as long in the y direction, and then Lz is 5 halves L, right? So it's 5 halves as long as the x side in the z direction, okay? All right, then part B, find the probability of finding the particle in a particular region, in this case in a region where x can vary between 0 and L over 6, and where there's no restriction on y or z. So it's going to be kind of like a slice, which I'll show a picture of. And that's going to be in this particular energy state. Okay, so the probability in that particular energy state. Okay, so let's do it. So the first thing we're going to do is we're going to point out that when we normalize the function, and actually this is the kind of the what I meant to include in my key equations, and I kind of had a combination of this. This is actually normalizing it. Here I have just a general integral. Truly it would be a triple integral in terms of x, y, and z, and it's over volume. And it's saying then that as we integrate that three-dimensional wave function over the total volume, that the probability has to be 1. And again, this is just saying that the particle has to be in the box. It can't be anywhere else, okay? So then here we do. We just set up the integral, okay? Notice all of our definite limits of integration, just based on the lengths of all the sides, okay? You're going to be doing a homework problem just like this, so follow through the steps. It's going to be equal to 1, okay? Because the particle can't be anywhere else. Now we're going to do our substitution. Okay, that's our trigonometric substitution. So I'm just going to replace all these sine squareds with this expression here. Okay, so that's all I've done in this line. That's all I've done, right? It looks long, but that's all I've done. Now again, I made the same mistake. These should all be 4s because I have to distribute in that 1/2. Okay, so stupid mistake, but again, it won't affect the results in this example. Okay, so now I'm going to argue for the upper and lower limits. Okay, so this one right here is going to be 0 for x equals L, or x equals 0 and x equals L, okay? Because if you substitute in the L, you get the exact same result that we had for our 1D box. You just have 2n times pi, all right? Because you'd have L over L, which would just cancel out. And so then 2n over pi is always going to be 0, because again, you know, sine of 2 pi is 0, sine of 4 pi is 0, sine of 6 pi is 0, and so on, right? Good. And again, nx is just a integer. The whole idea, the reason there's a subscript x is because now there's energy states in all three of the axes. There's an nx, an ny, and an nz, but they're all just 1, 2, or 3. They're just standing waves, but one aspect of a three-dimensional standing wave. Okay, same thing in y, but here it's different, right? Because we're substituting y equals 2l. So if you think about the upper limit in that case, if you plugged in an n of 1, and so if you substitute in 2l here, the l's would cancel. So an n of 1 would be sine of 4 pi. Well, sine of 4 pi is still an integer multiple of sine of pi, and sine of pi and 4 pi and 3 pi, they're all 0, right? Because sine returns to 0 every pi. So you're fine there, right? So it's still, you know, some integer times pi. So check out, it's still 0. The third one's the most interesting because then you're going to substitute in 5 halves. So then your z would be 5 halves L, your L's would cancel, your 2's would cancel, so then you'd have 5 nz times pi. Well, 5 nz times pi, although now it's an odd integer, is still an integer, so you're still going to have 0 at z equals 5 halves L. Now, here's the thing. That wouldn't work for all lengths of L. What if I had 7 6L, right? Well, that wouldn't work anymore, okay? 5 halves happens to work because the 2 cancels. But there are a lot of lengths that it wouldn't work, in which case this would stick around. It wouldn't be 0 for all values of energy states. And in that case, your normalization constant, C, is actually a function of the whatever energy integer is or does not cancel. And so it could be in the homework, for example, there's one of them that doesn't cancel, and thus your normalization constant is a function itself of one of the integers, either n sub x, n sub y, or n sub z. All right, which is pretty neat. Okay, so in this case, though, this is just the final result of all those integrals, right? Because again, it's really simple because the only part that's left are just these parts, and I just evaluate each of them at the upper limit. This one just becomes L over 2. If I evaluate this one at the upper limit, it's 2L over 2, which is just L after all. And then I evaluate this one at the upper limit, it'd be Z over 2, it would become 5L over 2, which is then just 5/4 times L. All right? That's all going to be equal to 1 because the probability of the particle being in the box is 100%. It's there, okay, somewhere. Okay, so then the real positive value of c squared is just going to be this. All right, and then we just take the square root, and that is our normalization constant for this particular shaped rectangular box. Okay? All right, so now we want to find the probability of the particle being in the shaded region, this one here. Because I asked, what's the probability of it being in this region, where x varies between 0 and L over 6. So that would be this little slice, right? Because I didn't give you any constraints on y or z. So that's why it's a full slice like that. Now I could have said, what's the probability of it being in a rectangular box where x varies between 0 and L over 6, and y varies between 0 and L, in which case it'd be just half of this, right? But I didn't. I just gave you a single slice. Okay, so then we're just going to do the probability. Okay, so here the probability isn't 1 anymore. Now we're going to solve for the probability, which we couldn't have done if we just had a constant c sticking around, right? But that's the whole point, is we found c, which means now that we've done the setup work, we can find the probability of the particle being anywhere we want. Any little subsection of the overall area shown in green. Okay, so it's pretty neat. You got to find the normalization constant first before you can answer any probability questions. Okay, so here we're going to find a probability. Notice that I just left these ones from the previous integrals since there's no constraint on z or y. They're just left as L and 5L over 4, okay? Because we already did the limits, the same limits. Here, however, going from 0 to L over 6 instead of 0 to L. Here is our normalization constant squared. That's our c squared, right? And so then we just go ahead and solve the integral. So I just do the anti integral here, and then I'm going to be evaluating from 0 to L over 6. Oh, I've already done it. So here I do 2 steps at once, okay? So I plug everything in, or I do the antiderivative. I use the trigonometric function where I get the whole 1/2 times 1 minus cosine 2 theta. And let's see, but it should be cosine. No, it's fine. It's 1 minus, oh yeah, okay. So 1 minus cosine of 2 theta. Interesting. I'm going to have to check that because here I have that I'm using so I wrote it as cosine, and cosine, Oh, right, of course, obvious. So excuse me for that. I got myself confused. So this is I'm often doing 2 steps at once, right? So here I do the trigonometric substitution, and then I take its antiderivative, which is why we get back to sine, which is also why we get this. All right, because of course when I do the antiderivative of cosine, I get positive sine, which is why the negative sticks around. Good. All right, so same thing here. I do the trig function, I do the antiderivative, and I've already evaluated the limits. That's why they're not shown there. And I evaluate the limit from 0, which just everything zeroes out, and then at the lower limit, but the upper limit sticks around as L over 6, which is why we get L over 12. And over here we have an L, and here I actually have the correct 4n pi, I believe. Yep. Which is good because I'm trying to get the correct number. Yep, L over 4n pi. Just want to double check that. Yeah. So it's funny, I didn't make the mistake there where it mattered, and I guess I was probably too fast and left the 2's there where they should all have been 4's. Okay. All right. So a couple typos to fix. All right. So anyway, then this is a couple steps, but all ready to just cancel out the L's, by the way, because the actual size doesn't matter. Just the proportions matter. So the L cancels out everywhere, as you can see. Okay. And then we clean it up a little bit. All I've done here is just kind of take my 8 and divide it by 4, which gives me my leading 2. I got my 1/12. Over here, now the energy state matters, right? Because I was told that I'm looking at the energy state of nx, ny, nz, right? Now the normalization constant was independent of the energy state, but the probability is not, okay? And so here, the 2 and 3 actually don't affect the probability because I didn't set any constraints on them. But the fact that we're in the fourth standing wave in the x component of our wave, of our three-dimensional wave, that does affect the probability, all right? And that means that nx equals 4, which means we have a 16 pi right there, all right? And so that ends up being 0.201, okay, for nx equals 4. And again, it would be, if we change nx, it would change the result, but if we change ny or nz, the standing wave integers for those components of the wave would have no effect on the probability. And this tells us, in plain language, that there's about a 1 in 5 chance of finding the particle in the leftmost sixth of the box, which is interesting because there's not a 1 in 6 chance. It seems like it's more likely to find it on the left than to find it on the right. And indeed, if we bear out the probabilities, that's the case. These waves are fundamentally lopsided in fascinating ways. You can imagine kind of representing them graphically, right? So, but there's our number, right? Hopefully it makes sense. The process is very procedural, and you're going to be doing this in the homework. So let me quickly speak to the homework, which I've hinted at. So in problem 1, consider a box with equal length sides. In this case, what is the probability to find the particle in the corner of the box in the region, so where x is restricted, y is restricted, and z is restricted. Essentially, it's 1/4 of the box, right? So if you took a cube and divided it into actually not 4. So if you divide it into 8s, it'd be 1/8 of the box. That, you know, kind of the lower x of the box. Think like a 2 by 2 by 2 Rubik's cube, if you've ever seen those, right? The smaller ones, and it'd be one little part of that, right? 1/8 of the overall cube. In this case, finding the normalization constant, again, you can easily check your work because this is the normalization constant for a cube, so it's a well-known one. All right, and then you'll do the same sort of thing. You'll do the integral to find the normalization constant, and then do the integral to find the probability. Okay, once you found the normalization constant. Okay, same thing in problem 2, but now we're back to a rectangular box. We've got different length sides, but notice this one is 5/7 now, not 5/2. Otherwise, it's basically the same as the example I showed you. All right. In this case, you're going to have a normalization constant that is going to be a function of, I'll just tell you, if you listen this far, of nz, okay? So it doesn't change anything. It means that so that means that your final, the constant is going to be a function. It's not just going to be a function. It's, like here, if we look, it's just a function of L. That's it, right? But here, it's going to be a function of L and nz. So C will be a function of L and nz, right? So that's what the form of part A. In part B, then since I give you a particular set of nx, ny, and nz, then you're just going to plug them in, which is going to affect your normalization constant. So plug in the nz right away, value of 6, to get your normalization constant as just a value, so that your L's can cancel out when you do the probability integral. And then at the final step, once you've done the integral, then you can plug in your nx, because I have the same restriction on x, and I don't set a restriction on y, so I bet you can guess how important that energy state in y is. Not at all important. Okay? All right, so those are some tips about the homework. Please have some fun with them, just dwell on this idea, and also just the fascinating mathematical process of it all. I'll fix those couple typos and get these post notes uploaded. Thank you so much for watching this final video for Physics 38.